Good morning, everybody. My name is Ettore Del Monte from INAF in Rome. I will introduce you to this experiment called LEM-x for astrophysics from the surface of the moon. I will start with a few words about the new era of multi-messenger astronomy and then the scientific requirements for an X-ray monitor on the moon. Then I will describe the design of our instrument, the development of the key enabling technology, and finally, I will draw my conclusions. So, as you already probably know, we are now in the era of multi-messenger astronomy. This means that in order to study astrophysical sources, we base not only on the detection of photons, but also of gravitational waves, neutrinos, and cosmic rays. All these type of phenomena are emitted by transient events and by variable sources. This means that in order to detect these phenomena, we need to monitor simultaneously a large fraction of the sky. The moon is very interesting from this point of view, since it offers a sort of a platform where we can install more instrumentation than on a satellite. And as I will explain you later in the presentation, the all sky coverage can be obtained by exploiting the rotation of the moon itself. These are our main scientific requirements. So we want to work in the X-rays in the energy band between 2 and 50 keV. And in this sense, the moon offers no atmosphere. The moon has no atmosphere to stop X-rays. We want to have a field of view of the order of 2 pi steradians to cover at least half of the sky. And here we know that we can put on the surface of the moon more instrumentation, larger instrumentation than on a satellite in orbit around the Earth. We will have an angular resolution of the order of 4 arcminutes for a camera pair, and the point source location accuracy of 1 arcminute. The energy resolution is 350 electron volt full width at half maximum at an energy of 6 keV. The sensitivity is corresponding to 1 crab, that is this number in CGS units in 1 second, and 5 times 10 to the minus 3 crabs in half a day. This is a sketch of our instrument. It is constituted of 7 pairs of coded aperture cameras. I will show the single cameras in a moment. And this is on a dedicated mechanical structure to be put on the surface of the moon. This is our concept. So the basic building pair is represented by building block is represented by a pair of cameras with the, I will explain in a moment, with the detectors rotated of 90 degrees, one with respect to each other. It is based on the heritage of the LOFT and EXTP previously studied projects. It is a coded aperture imaging camera in X-rays in the energy band between 2 and 50 keV. Each camera has a field of view of about 1 steradian and a point source location accuracy of 1 arcminute. The volume enveloping the camera is about 35 times 35 times 35 centimeters. The mass is roughly 18 kilograms and the power consumption is 15 watts. So the detectors are linear and large area silicon drift detectors, and the position resolution of each detector is non-symmetric. This means that we have a position resolution of the order of 25 microns in one direction and about 5.5 millimeter in the orthogonal direction. If we combine this type of detectors with a coded aperture camera at a distance of about 20 centimeters, we obtain an instrument with again, an asymmetric angular resolution of the order of 5 arc minutes time 4 degrees. A pair of cameras, so with detectors orthogonal, one with respect to each other, and observing the same field of the sky, can reach a point source location accuracy of the order of 1 arc minute. This is, as you can see from a simulation of an image of the galactic center, this location accuracy is adequate to resolve a crowded region such as the galactic center, which is of interest for X-ray astronomy since it is populated by many variable sources, and we are interested in keeping this under control and monitoring this in order to find, for example, transient events or maybe some spectral state change of one of these sources. Now the observing strategy. I have told you that we want to observe about 1/2 of the sky in order to provide the image of sources. Since from simulations of gravitational waves, the expected number of events in gravitational waves is extremely large with the new and improved instrumentation for gravitational waves. And when I say large, I say tens or even hundreds of events per day. You may understand that it is impractical to try to repoint X-ray satellites like, for example, the Swift Observatory, as it is done nowadays, in order to find the counterpart of such gravitational wave events. On the opposite, we plan to monitor about half of the sky, and when a transient event or a gravitational wave event is detected, we can find the simultaneous in time, the simultaneous event in time in our data, and find if we have the counterpart in X-ray directly in our data. This is one of the main goals of having a so large fraction of the sky monitored at the same time. We are still assessing the telemetry that is needed for this purpose, and this is part of our study. As an example, I show you on the left the exposure map that we obtain, a simulation, if we put such an instrument at the moon equator. The moon equator was the landing site, for example, of the Apollo missions. On the right, we have the exposure simulated for one of such monitors at the South Pole. So as you can see from the left image, we can monitor all the sky, this is in galactic coordinates, by exploiting the rotation of the moon itself. While, for example, on the pole, we can monitor only half of the sky with a slightly higher exposure. Now, few words about the development of the key enabling technologies for our experiment. So we use large area and linear silicon drift detectors with a geometric surface of about 45 centimeters square, sensitive area, and very small anode capacitance. These detectors, again, are on the heritage of the LOFT and EXTP mission that was studied in the past. We are developing a new and dedicated front-end application-specific integrated circuits specifically for these detectors and this instrument in order to have low noise and low power consumption. We are also developing a new digital converter, application-specific integrated circuit, to digitally convert the signals from the front-end ASIC, and a custom front-end board to integrate all these components. This will be the main requirement of this board is the capability to maintain the mechanical alignment from the thermal operative range between -55 and +30 Celsius. This is a schematic of what we are going to develop. You can see the front-end board with the silicon drift detector on the back and the ASIC on the sides. Connectors, a hybrid structure used as additional connector, and the dedicated thermomechanical structure. This is funded by the Italian Ministry for University and Research under the Next Generation EU, the so-called Programma Nazionale di Ricerca e Resilienza in Italy. My conclusions, I have shown you that multi-messenger astronomy requires an all-sky monitor. The moon offers a relevant advantage with respect to putting this instrumentation on a satellite in orbit around the Earth. Our design includes 7 pairs of coded aperture cameras to be put on the surface of the moon, and to achieve all-sky monitoring by exploiting the rotation of the moon itself. We are developing this instrumentation under these funds of the Next Generation EU. Thank you.